Okay, we're starting off a new chapter, Chapter 9, Differential Equations, which I label a very brief introduction to differential equations. For those of you who are taking multiple math courses here at ARC, you'll know that we offer Math 420 differential equations, which is your standard introduction to differential equations at the lower division math undergrad level. So let's get into it though. This chapter we're going to introduce formally differential equations, what we're trying to find, what the applications of them are, and some techniques for solving some very simple ones. So I'm going to start with a motivating example, which kind of historically is where we began actually with differential equations. So the thing you want to keep in mind is really where this comes from is from Newton's second law, which if it's been a while since you've taken physics, or even if it hasn't, let's just go over it briefly. Basically what Newton's second law of motion, this is a law of nature that Isaac Newton proposed, governs how all objects move with respect to a force applied to it, which is that the force that is applied on a object will dictate its acceleration. So roughly we can write that as F equals ma, which is another way of writing this is the acceleration due to a force is proportional to that force applied in that direction. Okay, so it's directional. We're not going to focus on that right now, but really what you want to think is our prototype here will be a ball that's being dropped off the side of a building. And so that ball has mass, right? So it's got mass. Maybe it's 10 kilograms, 15 pounds, whatever you want to call it, right? But when it falls off the side of the building, what causes its motion is the force of gravity. So the gravitational force pulls it down toward the center of the earth. And that force strength, like how fast it moves, is changing. And that force is given by the mass of the object times the gravitational constant, or the acceleration due to gravity, g, which is roughly 9.8 meters per second. Okay, but every object, regardless of where it is relative to the surface of the planet, experiences this same force, right? But we can write this law slightly differently. I know this feels long-winded, but let me get to the point of this. We can write this equivalently as F equals m times d2x dt squared, which in this notation, right, what we want to think about is the acceleration, right, as a function of time, okay, is a rate of change. And specifically, it's the second derivative of position. Okay? So really what this is helping us do, though, is if we can write this a little bit simpler, right? Let's write it as, I'm gonna flip it now. I'm gonna switch the order here. So mx double prime equals f. I'm gonna write x double prime equals 1 over m f. And that could be a function of x itself. It could be a function of time. We don't know what the force could be. It could be constant. It might not exist at all. But this right here, this sets up really the fundamental challenge of classical mechanics, which is to solve this differential equation. So this differential equation, switching out F for different forces, will it really sets up like the entire field. Okay, so let's see a concrete example. Right? I already talked about a ball bed getting pulled down by, so the simplest possible example, okay, is free fall, no drag, so no air resistance, okay? In that case, the force is just negative mg, okay, which is constant, okay? And so the corresponding differential equation is just x double prime equals 1 over m times negative mg or equals negative g. And as we could find out using our techniques with antiderivatives, this will give us some fundamental formulas that we can apply that you see on day 1 in physics. So that's the simplest possible example. If we instead have free fall with a high resistance drag force, okay, now what we're going to have is a different force. So we're going to have not only just the force of gravity pulling against it. So in this first case, right, we're just looking at this force, right, and there's no force that's pulling it in the opposite direction. And the negative sign there is because we're indicating that the down direction is negative, up direction is positive. Plus k times v squared, where, so this v is velocity, okay, which is x prime, okay, and this is just some drag coefficient, okay, so it is a constant. In other words, what this differential equation becomes, right, is x double prime equals 1 over m times negative mg plus kv squared. So it's going to be negative g plus k over m, v squared, okay? And we can write that actually as x prime squared. So now we have a differential equation that relates not only to the second derivative of x, but also the first derivative. And in fact, what we usually do is write v equals x prime. So going backwards now, instead of replacing v, we'll replace x double prime. We get v prime equals negative g plus km v squared, okay? And so we get an ordinary differential equation that is non-homogeneous of first order. Okay. So all of this is to set up the fact that we are going to be talking about the wonderful world of differential equations, and there's some terminology we have to get out of the way. We'll do that in the next video. And then we're going to start to talk about some pretty fundamental models that motivate the need for having to talk about differential equations, right? But we'll check that out in the next video.